Welcome to our deep dive into Gauss Theorem, a fundamental concept in the world of mathematics and physics. Whether you're a student, a science enthusiast, or just curious about how the universe works, understanding Gauss Theorem opens up a new perspective on electric fields and flux. In this video, we'll break down the theorem, explore its applications, and see why it's so crucial in both theoretical and practical context. Let's start by setting the stage and understanding the basics before we move into the heart of the theorem. Before we delve into the theorem itself, let's take a moment to appreciate the mind behind it. Carl Friedrich Gauss. Known as the Prince of Mathematicians, Gauss made significant contributions to many fields, including number theory, astronomy, and electromagnetism. His work laid the foundation for much of modern mathematics and physics. Understanding his background helps us appreciate the depth and elegance of the theorem that bears his name. At its heart, Gauss' theorem connects the concept of electric flux through a closed surface to the charge enclosed within that surface. It's a bridge between the microscopic world of charges and the macroscopic world of fields. This powerful relationship allows us to simplify complex problems and gain insights into the behavior of electric fields in various situations. Let's see how this connection is established. Electric flux is a measure of how much electric field passes through a given surface. Imagine a field of arrows representing the electric field lines. The more arrows that pass through a surface, the greater the flux. This concept is crucial for understanding how Gauss' theorem operates, as it quantifies the field's interaction with surfaces in space. A closed surface is like an imaginary bubble that completely encloses a region in space. Think of a sphere, a cube, or any shape that forms a boundary with no openings. Gauss' theorem specifically deals with these closed surfaces, as they allow us to analyze the total electric flux entering and leaving the region. Mathematically, Gauss' theorem is expressed as the total electric flux through a closed surface equals the net charge enclosed divided by the permittivity of free space. This concise equation captures the essence of the theorem and serves as a powerful tool for solving a wide range of problems in electromagnetism. To better grasp Gauss' theorem, let's visualize it. Picture a sphere with a charge at its center. The electric field radiates outward, and the flux through the sphere's surface can be calculated using the theorem. This visualization helps make the abstract concept more tangible and easier to understand. Gauss' theorem is especially useful when dealing with problems that have a high degree of symmetry, such as spheres, cylinders, or planes. It allows us to bypass complex calculations and arrive at solutions more efficiently. This makes it a favorite tool among physicists and engineers alike. There are three main types of symmetry where Gauss' theorem shines: spherical, cylindrical, and planar. Each type allows us to choose a surface that matches the symmetry of the problem, making calculations straightforward and elegant. Let's consider a point charge placed at the center of a sphere. Thanks to spherical symmetry, the electric field is the same at every point on the surface. Using Gauss' theorem, we can easily calculate the electric field without complicated integrals. Now, imagine a long, charged wire. Here, cylindrical symmetry comes into play. By choosing a cylindrical surface around the wire, Gauss' theorem lets us determine the electric field at any distance from the wire with remarkable simplicity. For an infinite plane of charge, planar symmetry is the key. By selecting a box-shaped surface that straddles the plane, Gauss' theorem helps us find the electric field on either side of the plane, demonstrating its versatility. Permittivity of free space is a constant that appears in Gauss' theorem. It quantifies how much electric field is permitted to pass through a vacuum. This constant is crucial for converting the amount of enclosed charge into the resulting electric flux. Gauss' theorem is often written in its integral form, which involves integrating the electric field over a closed surface. This mathematical expression elegantly captures the relationship between fields and charges, making it a cornerstone of electromagnetism. There's also a differential form of Gauss' theorem, which relates the divergence of the electric field at a point to the charge density at that point. This form is especially useful in advanced physics and engineering contexts. Physically, Gauss' theorem tells us that the total number of electric field lines passing out of a closed surface is proportional to the total charge inside. This intuitive picture helps us visualize how charges create fields in space. Gauss' theorem isn't just a mathematical curiosity, it has real-world applications. It's used in designing capacitors, understanding electric shielding, and analyzing charge distributions in various devices. Its utility spans from classroom problems to cutting-edge technology. In capacitor design, Gauss' theorem helps engineers calculate the electric field between plates, ensuring devices store and release energy efficiently. This practical application highlights the theorem's importance in everyday electronics. Electric shielding, used to protect sensitive equipment from external electric fields, relies on Gauss' theorem. By understanding how charges distribute on surfaces, engineers can design effective shields for a variety of applications. Gauss' theorem is invaluable for analyzing how charges are distributed in conductors and insulators. It allows scientists and engineers to predict field behavior and optimize material performance in various devices. While Gauss' theorem is powerful, it's not always applicable. It works best when there's symmetry in the problem. For irregular shapes or non-uniform charge distributions, other methods may be more suitable. A common misconception is that Gauss theorem can be used for any problem involving electric fields. In reality, its power lies in situations with symmetry. Recognizing when to use it is key to solving problems efficiently. Gauss theorem has had a profound impact on the development of physics and engineering. Its introduction marked a turning point in how scientists approached electric and magnetic fields, paving the way for modern theories. Gauss theorem is one of Maxwell's four equations which form the foundation of classical electromagnetism. Its inclusion highlights its central role in understanding how electric fields behave in the universe. There's also a Gauss law for magnetism, which states that the net magnetic flux through a closed surface is always zero. This reflects the fact that magnetic monopoles have not been observed in nature. Interestingly, a similar theorem applies to gravitational fields. Gauss theorem for gravity relates the flux of the gravitational field through a surface to the mass enclosed, showing the theorem's broad applicability. The proof of Gauss theorem involves calculus, particularly the divergence theorem. By relating the surface integral of the field to the volume integral of the charge density, the proof elegantly ties together geometry and physics. The divergence theorem is a mathematical result that connects the flow of a vector field through a surface to the behavior of the field inside the surface. Gauss theorem is a specific application of this broader principle. Understanding surface and volume integrals is key to mastering Gauss theorem. Surface integrals measure the total field passing through a surface, while volume integrals sum up properties within a region. These tools are essential for applying the theorem. Selecting the appropriate Gaussian surface is crucial for simplifying calculations. The best choice matches the symmetry of the charge distribution, making the math much more manageable and the results more insightful. Let's work through a practical example. Suppose you have a point charge at the center of a sphere. Using Gauss theorem, you can quickly calculate the electric field at any point on the surface, demonstrating the theorem's power and simplicity. Now, consider a long, uniformly charged cylinder. By choosing a cylindrical Gaussian surface, Gauss theorem allows us to find the electric field at any distance from the axis, showcasing its utility in real-world scenarios. For an infinite plane of charge, Gauss theorem simplifies the process of finding the electric field above and below the plane. This example highlights the theorem's effectiveness in handling large, uniform distributions. When dealing with non-uniform charge distributions, Gauss theorem may not always provide a straightforward solution. In such cases, more advanced mathematical techniques or numerical methods are required. Visualizing electric field lines helps in understanding how Gauss theorem works. Field lines radiate from positive charges and converge on negative charges, and the number of lines through a surface relates to the enclosed charge. Direction matters in Gauss theorem. The orientation of the surface and the direction of the electric field determine whether the flux is positive or negative, affecting the final calculation. The size and shape of the surface directly impact the total flux. Larger surfaces capture more field lines, while the shape can influence how the field interacts with the surface. This is why choosing the right surface is so important. Only the charge inside the closed surface contributes to the net flux. Charges outside the surface have no effect on the total flux through that surface, a key insight provided by Gauss theorem. In electrostatics, conductors have unique properties. Gauss theorem helps explain why the electric field inside a conductor is zero and why excess charge resides on the surface. For insulators, Gauss theorem helps analyze how charge is distributed throughout the material. Unlike conductors, charges can be spread throughout the volume, affecting the resulting electric field. Gauss theorem isn't just a theoretical tool, it describes real phenomena in nature. From the behavior of storms to the structure of atoms, the theorem's principles are at work all around us. In advanced physics, Gauss theorem is used in fields like plasma physics, astrophysics, and quantum mechanics. Its versatility makes it a cornerstone of scientific research and discovery. Let's recap what we've learned. Gauss theorem connects electric flux and enclosed charge, simplifies calculations in symmetric situations, and has wide-ranging applications in science and engineering. Understanding its limitations and proper use is essential for mastering electromagnetism. For those interested in exploring further, there are many excellent textbooks and online resources on Gauss theorem and electromagnetism. Delving deeper will enhance your understanding and open up new avenues of discovery. Thank you for joining us on this journey through Gauss theorem. By mastering this fundamental principle, you're better equipped to tackle challenges in physics, engineering, and beyond. Keep exploring, keep questioning, and let the beauty of mathematics inspire you.